Dear students, welcome to the next lecture of microcontrollers. So today we will start with one of the special function registers. So in your last lecture, if you recall, we mentioned that we will study the special function registers in detail while we will go through the related lectures in future. So today we will study one of the special function registers, which is called PSW, or program status word. Okay, so let's see what is the functionality of PSW. So the program status word or PSW register is one of the many special function registers in the 8051. So as you saw, there are a lot of special function registers. So PSW is one of them, and it is an 8-bit register. So 8-bit 8051 is an 8-bit microcontroller. So PSW is an 8-bit register, and this is also sometimes referred to as flag registers. So basically it contains different bits that indicate certain conditions has resulted or not. Okay, so only 6 bits of these registers are used by the 8051. The other 2 can be user defined flags. So you can define your flags, okay, using the 2 of the bits of PSW, and you can define it in your assembly language code. So, and the 6 bits of the registers are used for different operations and to raise certain condition within the microcontroller, like if different functions are executed, then there would be some conditions related to those functions that may be necessary to perform some other functions. Okay, so for example, let's say you want to monitor after addition of 2 numbers whether there is a carry or not. Okay, so in that case a carry flag will be there that will be activated, and then using that information you can do something else. Okay, so 6 of those bits in the PSW are used for these type of operations, and 2 are user defined. So as I was saying, so there is one carry flag here. Okay, so CY, this is the bit 7 of the PSW register. Then the bit 6 is the auxiliary carry flag. Okay, then you have F0, which is the first of the 2 user defined flags, and then you have F1, which is another user defined flag. Then RS1 and RS0, these are the 2 flags that are combined together to select, the register banks. So you remember there are 4 register banks, okay, in your 8051, and each of those register banks had 8 registers. So there were total 32 registers, right? So the 8 registers are defined as R0, R1 up to R7, right? So when you are using a register R0, let's say you are writing an instruction move something to R0, let's say a number 10 to R0. Okay, so when you are using this name, this can be the R0 of register bank 1, or this can be the R0 of register bank 2, or this can be the R0 of register bank 3. So there are 4 register banks. So how do you know which register banks R0 you are using. So for that you are using these two flags of the PSW register RS1 and RS0. So if you select these, the combination of two bits in a way that, let's say, if it is 0 0, if these two bits are 0 0, then you are selecting register bank 0. Okay. If these two bits are 0, this is 0 and this is 1, then you are choosing register bank 1. Okay. If this is 1 and 0, then 2, and if this is 1 1, then 3. Okay. So depending on the combination of these two bits, whatever the binary combination of these two bits suggests, you are choosing that register bank. So 4 register banks and 2 bits can have 4 combinations, so it can help you selecting the register banks. Then you have the overflow flag and then the parity flag. Okay, so let's see the detailed function of these flags. So in case of a carry flag, as I said, this flag is set whenever there is a carry out from the MSB after addition or subtraction. So it can be set and reset using the single bit instruction. So you can set the carry flag to 1, you can clear the carry flag if it has been set. But it is automatically set if there is a carry from the MSB. So we can represent any byte as this, so D0 to D7, in which case the carry flag is set if there is a carry out from D7. Okay. And the auxiliary carry flag, the purpose of this is to see if there is a carry from bits D3 to D4. So from the first nibble to the second nibble, so from D3 to D4, if there is a carry, then this auxiliary carry flag will be set. Okay. So it can be set and reset also using a single bit instruction like this, set and clear, set B and clear. Then comes the parity flag. So this flag is set if the number of ones in the accumulator is odd. Okay. Otherwise it's 0. The overflow flag, this is set whenever the result of a signed number operation is too large, causing the MSB to overflow into the signed bit. Okay. So there is a subtle difference between this overflow flag and the carry flag. Carry flag is for unsigned numbers, addition and subtraction. If there is a carry, then the carry flag is set to 1. But in case of signed number operation, if there is overflow into the signed bit, then this overflow flag will be set to 1. So let's see an example. So determine the state of these flags, carry, auxiliary carry and parity flags, after the following code has been executed. So this code is basically adding these two numbers. Okay, you are moving this number to the accumulator and then adding the next number with the contents of the accumulator. So basically it is doing this plus this. Okay. So if you do this addition, okay, if you do this addition, then you will get this number, okay, which is binary represented as this. Okay. So if you do this addition, you will see that there is no carry. Okay. So therefore the carry flag will be 0. If you again do this addition, then you will see that there is an overflow. There is a carry from D3 to D4. Okay. So the auxiliary carry will be set to 1, and after the final addition, the accumulator will be storing this result, and this has 1 2 3 4 5, so odd number of ones, so the parity flag will be set to 1. Now let's check another example. What will be the contents of the register A after the following instructions? So basically this is adding two numbers, 79 hex and F5 hex. So as we all know that by now that the 8051 is an 8-bit device, so this means the majority of the registers are 8 bits. Okay, there are exceptions, so the program counter and the DPTR, they are 16-bit registers, but for many applications 8 bits is sufficient, and there could be some exceptions to this. So sometimes we can run into problems where 8 bits are not enough. For example, if you do this sum in this example, okay, then you will see that the result is greater than 8 bits. Okay, so in that case the accumulator overflows, and this raises the question, therefore, can we perform arithmetic with values that yield greater than 8 bits? And the answer is yes, and we will see how that is done. And now you will find out a very good usage of this carry flags and the auxiliary carry flags. Okay, so let's look into this example code. Write an assembly code to add the two 8-bit numbers 79 and F5. Display the 16-bit result. So by now you know that if you add these two numbers, it will be more than 8 bits, so you have to represent it in a 16-bit format. Okay, even if there is a overflow of 1 bit, so let's say these are your bits of the 8-bit registers. Okay, so let's say this is your D7. Okay, so if there is a carry here, even 1 bit, let's say 1, after adding these two numbers, the accumulator will have this, let's say this 8 bits, and then there, let's say there is a overflow 1, or there is a carry, then this carry has to be accommodated in another register. Okay, even there is a 1-bit carry that has to be here, and then the rest will be, let's say, 0. Okay, so we have to use another 8-bit register to store the final result, which is 16 bits. So this 8 bits where, let's say, everything is 0 except this, and then this 8 bits. Okay, so there has to be 16-bit result. So display the 16-bit result in R1 and R0. So R1 will contain your LSB, so this will be moved to R1, and R0, which are the MSBs, they will be here. Okay, so this will be R0. Okay, taking into account any overflow that occurs. Okay, so the way you can write this type of code is, well, first it's already mentioned that R0 and R1, these two registers will be required, so you initialize these two registers by clearing them, which is equivalent to moving a 0 to these registers. Okay, so then you move your first number in the accumulator, add that second number with the contents of the accumulator. So basically this is happening in this line. Now you have to check whether there is a carry or not. Okay, so you saw that at the end of the last lecture we were discussing about some jump instruction. So you are using this particular instruction JNC, which means jump if no carry. Okay, and then it will automatically check the status of the carry flag, and in this case if you add these two numbers, there will be definitely a carry, and the carry flag will be set to 1 after this step. Okay, so now here you are checking jump if no carry. So in this case there is a carry. Okay, so if this was there, if this addition didn't give me any carry, this carry flag would have been 0. Okay, and it would have jumped to this line which is labeled as no carry. Okay, and what this line is doing, it's just moving the final result in A to R1, and remember R1 will contain the LSBs. Okay, so if there were no carry, then we have only the LSBs. Okay, we don't have anything here in this register. Okay, if there were no carry, so only the contents of the accumulator are moved to R1. So that is happening here. But if there is a carry, which is the case for this example, so in that case this instruction will move the program to this line. Okay, because this means only jump if no carry. Okay, so if there were no carry, then it would have jumped here, but since there is a carry, it will go to this line and it will increment R0. Okay, so if your carry is 1, which is the case, then R0, which was all zeros here, R0 was initially all zeros. Okay, because you have initialized R0. Okay, so now it's incrementing R0 and it's becoming 1 here. Okay, so that's how the carry is accounted for, and whatever be the added number, the LSBs are there in your accumulator. Okay, and that result is moved to R1. So your R1 will have the 8 LSBs of your addition, and let's say this is your R0, and because of this your R0 will have the 8 MSBs, right? And in this case the 8 MSBs are only 1 here and rest are 0. Okay, so this is how you are using two registers to store the result of an addition which is more than 8 bits, and to check and take count of the carry, you are using this instruction JNC. Okay, no carry. So this is a smart way of keeping track of the carry and then incrementing the other registers, so that you have all the bits of the final result restored. So let's say now if we extend this concept to the addition of 3 numbers, so in the case of 3 numbers, you will have the same concept. So first you add these 2 numbers. Okay, and then you keep track of the carry. Okay, and then you add the next number, and then you keep track of the carry again, and you can use the concept that is shown in the last program and extend it further to add any numbers that are 8-bit, but the final results may be more than 8 bits. So here also you see that the result will be stored in R1 and R0. Okay, so since R1 and R0 is used, they are cleared. Okay, now you move the first number to the accumulator, you add the second number to the contents of the accumulator, which contains this number. So after this step you will have this operation, and then you are checking whether there is a carry. Okay, so if there is no carry, then you are moving to the next step, which is adding the third number to the accumulator. Okay, But if there is a carry, then you should increment R0 because R0 will contain your MSBs. Okay. Now after addition of the third number, you again check the status of the carry flag. So again you use the JNC command, and this time with a different line or different label. So after the addition of the third number, if there is no carry, then you move to this line, which is the final step of this code, that is to move whatever is the result in the accumulator to R1. Now if the result after adding these three numbers is still 8 bits, then R1 will contain those 8 bits. Those are the LSBs. But you are checking the carry flag twice, once here after adding the first two numbers and another time here after adding the third number, and each time if there is a carry you are incrementing R0. So every time there is a carry you are incrementing R0. So if your R0 is like this, and let's say after the addition of the first two numbers there was a carry, so it would be here, and the rest of the numbers will be all zeros, let's say. Okay, and this was your accumulator, which is finally moving to R1, right? But then after this step, if there is another carry by adding the third number, then your R0 is getting incremented again. So your R0 will now become, let's say, like this, and the rest of the numbers will be 0, and the R1 will be the remaining 8 bits in A. Okay, so your R0 and R1 combined will give you the final 16 bits after adding these three numbers. So you can now see that you can extend this concept for multiple numbers. If you are asked to add 10 numbers, then you can still do that. You can write a loop and then you can add all those 10 numbers, and every time you check the carry flag to see if there is a carry, and if there is a carry then you increment the register that is meant to keep your MSBs of the final result. In this example, that is R0. And if there is no carry, then you keep doing the next steps which you are supposed to do. Okay. So next we move on to the call instructions. So before doing that, let's check this example. So this is an example of a C code, okay, where you are trying to find out if a number is even or not. Okay, and for that usually you write a different function which is checking if the number is even, and if it is even then it returns 1, if it is not then it returns 0. Okay, so every time in your main code, if you want to check a number whether it's even, you can call this function many times. Okay, so the same concept can be extended in case of your assembly language coding. So in assembly language coding you use a call instruction, okay, to call a subroutine. So the function that is there in your C coding concepts is there in your assembly language coding also. In your assembly language coding you call that as a subroutine, and you can use the call instructions to call these subroutines inside your main program or inside your main routine. Okay, so here is an example. So in your 8051, by the way, there are two types of call instruction. One is a long call and the other is a absolute call. We will examine each of these in turn. So let's first focus on L call. So in this example we will use a subroutine to add the number in R1 to the accumulator 7 times. Okay, so so let's say my name of my subroutine is sum. Okay, so in this subroutine sum, you are adding the number in R1 to the accumulator 7 times by using this loop. So you learned about dj and z in your last lecture. So dj and z is actually checking this counter which is set in R0. Okay, and in this case it is 7 times. So you initialize R0 with 7 and then you are checking whether R0 is going to 0 or not. You are decrementing and then checking whether it is 0 or not. So as long as it is not 0, it is jumping to this line loop and it is doing the same addition 7 times in a loop. Okay, so then it returns. So see, in your original example of the C code, you had a return command that was or return instruction that was helpful for the function to return to the main code. Here also we use the return concept by this instruction RET. So this will return to the main code, and in the main code we are doing nothing but you are clearing the accumulator and then you are moving 1 to R1, because let's say you have to have some number in R1 which you are adding 7 times. So let's say that number is 1. Okay, and then you are calling using the lcall instruction. You are calling the sum subroutine which is doing the looping of 7 times or the repeated 7 time addition, and then you are moving the contents of the accumulator to R2 in your main program. So after calling the sum subroutine, your accumulator will contains the 7 times addition of this number. Okay, so in this case this is 7 because 1 added 7 times is 7, and that final number has to be moved to R2 because that's what the code wants you to do. Okay, so so this is an example how you are using the lcall instruction to call a subroutine. So let's look into the details of lcall. So lcall is a 3-byte instruction, by the way. So the first byte is the opcode, okay, and the second and third bytes are for the address of the target subroutine. Okay, so second and third byte combined together is a 16 bits, and these are used to specify the subroutine address, and therefore the lcall can be used to call subroutine located anywhere within the 2 to the power 16 byte address space of the microcontroller. So the opcode for lcall is 12 hex. Okay, so if you recall from the first few lectures, every instruction that you can write in this manner has an equivalent hex or binary opcode, okay, which you are storing in your memory. Okay, so in this case, your 12H, the opcode for lcall, is stored in the memory location 0004. Okay, so you read from this side 0004. So this is your lcall opcode, and the next 2 bytes that follows gives you the address of the subroutine. Okay, so if you just start from 0000, okay, if you start your code from 0000 like this, so this is your move A. This is a 2-byte instruction. Okay, so you can see that the 2 bytes corresponding to the first instruction, move to A, is here. Okay, so this is the opcode and this is the data that you are actually moving. You are moving 00 to A. Okay, So the first 2 bytes is gone for this. The next instruction start from 0002, and this is also a 2 byte instruction. So the next 2 bytes are this. The opcode for move R2 A is 79. Okay. Sorry, the opcode for move R1 1 is 79, and this is the data that follows. And then comes your L call, which has an opcode of 12, and then the next 2 is the subroutine address. Okay, so if you see, here is the subroutine address, that the starting address of the subroutine. Okay, so that is denoted by the 2 bytes just after L call. Okay, so here if you look into the code, you are writing L call, and then you are writing sum here, which is basically moving to this line which is labeled as sum, or in other words, this is actually moving to the 2 bytes that is denoted right after the L call opcode. So these are the 2 bytes right after the L call opcode, and that is 0008, and it is basically moving to 0008. Okay, so this is how L call works, and then after that you have the other instructions. So these are basically this move from 0008 to the next few lines. So from 0008, this is your 0008. From here to the next few lines, you are having these lines. Okay, whatever the opcodes and the operands related to these. But here in the main code, after the L call, okay, so L call is a 3 byte instruction, the opcode and the 2 bytes to denote the subroutine. So after this line, you have this line which is 0007, 3 bytes after this 0004, that contains the next line which is move R2A. So move R2A, this instruction is stored at 0007. So this is the instruction for move R2A. This is the opcode related to move R2A. And then from 0008, your whatever is there is basically the addition of 7 times. These are the instructions equivalent to that. Okay, so so now let's move to the A call instruction. So in case of A call, you can have the same code. You write A call sum, and then you go to the sum subroutine, and it's doing the same operations. So basically adding R1 to A 7 times. Okay, so what actually has changed? Basically the change is that A call, this is a 2 byte instruction. Okay, so so after the first 2 lines, which takes 2 bytes each, the 4th line or 0004 location of the memory contains the A call instruction, and A call is a 2 byte instruction, unlike L call, which was a 3 byte instruction. So these 2 bytes are actually related to A call. Okay, so the first change is that we have saved 1 byte of memory, and the memory contents at address 0004 has changed from 12H to 11H. Okay, so in general, the A call instruction calls a subroutine located at the specified address, and the program counter is incremented twice to obtain the address of the following instruction. Okay, so so how the address of the subroutine is calculated, that is very important, and that's a bit different in case of a call. Okay, so in case of L call, it's just the next 2 bytes followed by the L call. Okay, so it was L call sum, or in other words it was like 12 and then whatever are the next 2 bytes here. So in that case it was 0008. Okay, so in case of A call you have only 2 bytes. Okay, so again look carefully, in case of L call you have 2 bytes just following the opcode. So it was a 3 byte instruction, 1, 2 and 3, and the 2 bytes just after the opcode was your subroutine address. But in case of A call you see it's a 2 byte instruction. So how do you find out the subroutine address out of these 2 bytes? Okay, so that has a trick. Okay, so let me explain that in detail. Okay, so let's say in general, so this is the general expression of an A call instruction. So A call is 2 byte, so let's say these are the 2 bytes of A call, byte 1 and byte 2. So byte 2, imagine that the 8 bits of byte 2 are A0 to A7. Okay, and byte 1 looks a little bit different. The first 5 LSBs of byte 1 is always this 1 0 0 0 1. Okay, this is fixed, and then let's say the next 3 is A8, A9 and A10. Okay, so you can see that in an A call instruction, which is a 2 byte instruction, you have A0 to A7 and here A8, 9 and 10. So you have 11 bits that are characteristic bits of an A call instruction, because these bits are fixed. So in any A call instruction, this is the general look or general structure of the A call instruction, the 2 bytes of an A call instruction. So you have A0 to A10, these 11 bits that are different depending on where your A call instruction is residing and which subroutine it has to call. Okay, so let me explain it in detail. So let's say my A call instruction, if it looks like this, then your subroutine address can be decoded from the bits of A call. Okay, so these are my A call bits. Okay, this is the first byte, this is the second byte. The second byte has 8 bits, A0 to A7. The first byte has also 8 bits, but then the 5 MSBs are fixed as 1 0 0 0 1, and then I have these 3 bits. Okay, so my subroutine address will be all these 11 bits here, A0, A1, A2, A3, A4 up to A10. So there are 11 bits here, and the remaining 5 are the 5 MSBs of the program counter. Okay, so when you are calling the A call instruction, if you go there in this line, A call 0004 is the starting address of A call. So after this A call instruction is executed, your program counter will increment 2 times to point out to this line, because whatever is in the program counter, that is the next location of the next instruction. So after A call is executed, your program counter will be incremented twice and it will be pointing to this line. Okay, So after the program counter has been incremented twice and it is locating in this line, whatever is the content of the program counter, okay, so in this example the program counter's content, the 16 bit of the program counter will be containing these number, okay. So this is basically 0006 in hex, or let's say this is 0, 0, 0 and 6. Now if you break this into 4 bits, then this is 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, and then this is 0, 1, 1, 0. So these will be the 16 bits of your program counter after it has incremented to 2 places, okay. So remember this. So after the program counter has been incremented, whatever is the first 5 MSBs, okay, those 5 MSBs and then A10, A9 up to A0 of the ACALL instruction, that will be your subroutine address. So this entire thing is your subroutine address, okay. So if you go back to that scheme here, so your subroutine address is given by A0 to A10 and then the 5 MSBs of the program counter after it has been incremented twice. And the twice comes from the fact that ACALL is 2 bytes, and whenever the ACALL instruction is executed, the program counter will automatically increment twice to locate to the next instruction, okay. So in the example of the code, you saw that the ACALL instruction was 1107, okay. So if you write it in binary form, you will get it like this. So this is 11, this is 1, and then this is 1, okay, and then this is 0, and this part is 7. So 1107 was your ACALL instruction. These are the 2 bytes of your ACALL in the example, okay. So these are the 2 bytes of your ACALL, okay, 1107, okay. So therefore the subroutine address will be, so now recall again, the program counter after moving 2 places was pointing to 0006. So the first 5 MSBs of the program counter was all zeros, 0, 0, 0, 0, okay. So these 4 zeros and then this 0, okay. So 5 zeros. So those 5 zeros will come here. So this is your program counter 11 to 15, and if you take all the other bits from your ACALL, so your ACALL is like this general expression. So this is your A0, this is your A1, and so on, this is your A7. So so all these will come here. So and then your A8, 9, 10 is these 3, okay. This is your A8, this is your A9, and this is your A10. So program counter 11 to 15, they were all zeros as I showed you. These A8, A9, A10 is 3 zeros, so they are here. And then A7 to A0 is just the byte 2 of the ACALL instruction. So that comes directly here, okay. So if you now combine everything, this is basically 07 or 0, 0, 0, 7, okay, and that is the starting address of your subroutine, okay. So this is your subroutine start, and if you now verify that indeed is your starting address of the subroutine, okay. So this is how ACALL instruction works, and it's a bit different and also slightly complicated, not so straightforward as LCALL. Okay, so I'll post another tutorial to explain how ACALL works using software simulator for the microcontroller. So now let's do another example to get our concepts of this ACALL a little firmer. So here is the program, and in 0024 it starts from 0020. So the first 2 bytes are these. Then the next line will be 0022, because starting from 0020 you have 2 bytes of this instruction. So the next line is this, which is also a 2 byte instruction. So the next line will be at 0024, and there is your ACALL instruction. Okay, and ACALL is calling this subroutine sum that is starting from 0140. Okay, so in the previous example we showed the mapping between the bits of the ACALL instruction and the subroutine address. So here the subroutine address is given, which is 0140. You have to find out what will be the 2 bytes of this ACALL instruction that is there in the memory location 0024. So that's what you have to find. Determine the memory contents at address 0024. So at 0024 you have ACALL sum, and what will be the 2 bytes of ACALL if your subroutine address is 0140. So you can do the same logic here. So 0140, these are the 16, this is in hex, so these are the 16 bits of your subroutine. So if you write it in binary form, this 0 will correspond to 4 zeros, this 1 will be this, then the 4 will be this, and then the zeros will be this. So this is your 16 bits of the subroutine address. So if you recall, the 8 LSBs are basically your A7 to A0 of the ACALL instruction. So here in this case you have 0, 0, 0, 0, 4, and yeah, so these 8 are your A0 to A7. Okay, now your subroutine address is now formed by this 5 is your program counter, 15 to 11, right? And sorry, and these 3, these are your A10, A9 and A8. Okay, so basically your ACALL instruction is basically 0, 0, 1, these are the 3, and then this is the fixed bits. So if you recall, the 1, 3 zeros and 1, these are the fixed bits. Okay, so you have A8, 9, 10 given by these 3. So A8, 9, 10, then these are the fixed, and then will come these 8. So 0, 1, 0, 0, and then 0, 0, 0, 0. Okay, so what does that mean? That means that this is 4, this is 0. Now if you look at the 4 bit each, then this is 1 and this is 3. So basically your ACALL instruction will be 3140X. Okay, so that's what should be your X and Y. So your X will be 3 1 and y will be 4 0. Okay, so that is what we have worked out with. So your x will be 3 1 and y will be 4 0. So that's how it works. Okay, we will do more examples and I will post a tutorial also to get this concept clearer. So therefore these are the final 8 bits of the the final 16 bits of the ACALL instruction. So this is your ACALL. Okay. So there are conditional jump operations and call operations also. So you have two unconditional jump operations, a long jump and short jump. The first is called a long jump because it's a 3-byte instruction. The second and third byte obviously gives you the 16-bit address where you need to jump. And the second call is called a short jump, and this is a 2-byte instruction. The first byte is the opcode and the second byte is a relative target address with value between 00 and FF. So what does this mean? This means, like, let's say when performing a jump, this byte is added to the program counter value, ignoring any carry produced. Okay, so let's say your short jump, you are using this. Okay, so short jump has some opcode. This will be 1 byte. Okay, and the next byte, so this is, let's say this is whatever be the byte, 1 byte, and the next byte, the second byte will be some number between 00 to FF. Okay, and whatever is that number, that is added to the program counter. Okay, so let's say, see with an example. So let's say you have a code like this. Okay, so it starts from 0000 and then at 0002 you have this short jump. So 0000 is move A with 01. So the opcode for this is 74. It starts in 0000. Okay, and 01 is the next byte because that's the data. So 2-byte instruction, the 2 bytes are these, and then for the S jump, which starts at 0002, the opcode is 80. Okay, now the question here is what will be here so that it can jump to this line. Okay, and this line starts from 0018. Okay, so whatever was mentioned in this slide is that the immediate 2 bytes that should follow the opcode for short jump, which is 80, is the absolute value that you need to add to the program counter so that it can move to this line. Okay, so after you execute this line 0002, okay, this is a 2-byte instruction. Okay, so you see 80 and then this unknown byte, we are going to determine this unknown byte, but in general the short jump is a 2-byte instruction. So the next line will start from 0004, whatever be that line, let's say. Okay, so the program counter after this instruction is executed, the program counter will point to 0004. Okay, so what you need to add to this program counter whose current value is targeting to 0004 so that it can reach to this line, so that will be 0014 and then only it will be 0018. Okay, so the immediate next byte will be basically 1 4. Okay. So if it is 1 4, then that will indicate that that is the number which will be added to the program counter, ignoring any carry, of course. That will help you to jump to this line 0018. So that is what it was said. So the second byte is a relative target address. Okay, this is not the absolute target address. This is a relative target address with value between 00 to FF. So when this jump instruction is performed, this byte is added to the program counter value, ignoring any carry produced. Okay, so that's what is happening. So 1 4, which is here, is added to the program counter to jump it to 0018. Okay, so that's the final number here. So I will give you a class exercise to solve. Okay, so that will use all the instruction that you learned so far: lcall, djnz, return, move, etc. So the exercise is to write a subroutine that implements a delay by counting down from 255 and returning when the counter reaches 0. Okay. So try this yourself, and we can discuss it in the live interactive session, or you can just post your solutions to me or email me. So I'll stop here today, and I will see you in the next lecture. Thank you.